Hey guys, welcome back to the course. I hope you are excited to move forward into deep learning. This section is going to be very exciting as you're going to be classifying a new type of data set. Let's jump right in. The data set that you're going to be classifying is referred to as the MNIST dataset. If you've taken any of my deep learning courses before, chances are you're already quite familiar with the MNIST dataset. In which case, feel free to skip the theory part of this section and simply move on to the code implementation. Otherwise, if you're unfamiliar, the MNIST dataset can be found online, and it's essentially just a database of various handwritten digits. The MNIST database has a large amount of data and is commonly used to demonstrate the true power of deep neural networks. As an example, take a look at the following figure. When you look at this image, your brain and eyes work together to recognize this image as the number 3. Your brain is a very powerful tool and is capable of categorizing this image as a 3 very quickly. This is all the more astounding when you see that the simple letter 3 can be written in so many different forms. These images are direct samples from the MNIST database and demonstrates the variety among different handwritten forms of different letters, or numbers I should say. The human brain can still classify all of these images as a 3 relatively quickly. Unfortunately, this task is not as simple for a computer to complete. It is only with the help of a deep learning neural network that allows you to train a computer to effectively classify these handwritten digits. So far, you have only dealt with data that contains simple data points on a Cartesian coordinate system. Notice that this class is a multi-class dataset and differs from the usual binary class datasets that we've dealt with in the last section. When dealing with multi-class data, one typically makes use of the softmax activation function in the output layer, rather than the typical sigmoid function that we discussed earlier. The sigmoid function is quite useful for classifying binary datasets. We used it earlier and it was quite effective in ranging probability values between 0 and 1. As effective as it was, now we make use of a new activation function that is capable of dealing with multi-class datasets, the softmax function, whose theory I have not included in this section. If you are interested in the theory for the softmax function, it can be found in the appendix of this course. I didn't include it in this section simply because its implementation will occur under the hood once we start training our neural network to classify this multi-class. Again, if you are interested in the theory, feel free to refer to the appendix. The MNIST dataset is a multi-class dataset, which consists of 10 classes into which we can classify numbers from 0 to 9. The major difference between the datasets we have used in the past and the MNIST dataset is the method in which the MNIST data is inputted into the neural network. The data we are used to is a set of data points that were each defined by a simple x-coordinate and a y-coordinate, or in this case, I guess, x1 and x2. This meant that the input layer simply needed 2 nodes for inputting a single data point. This actually changes when you analyze the MNIST dataset. For the MNIST dataset, a single data point comes in the form of an image. These images contained in the MNIST database are typically 28 by 28 pixels, 28 pixels traversing the horizontal axis, and 28 pixels traversing the vertical axis. This means that a single image from the MNIST database has a total of 28 by 28, which equals 784 pixels that must be analyzed. This means that the 28 by 28 image can be any random combination of brightness values among the 784 pixels. In order for our neural network to analyze one of these images, it must contain 784 nodes on the input layer. Due to the additional input nodes and the increased number of classes that the numbers can be classified in, 0 to 9, it is clear to see that our dataset is more complex than any of the datasets we've analyzed before. Classifying this dataset is going to require a deep neural network with the use of some hidden layers. Our neural network will look like this. It will have an input layer containing 784 nodes, a few hidden layers that feed forward the input values, and finally an output layer containing 10 nodes for each of the respective handwritten numbers. The values are fed through the network, and the node that outputs the highest activation value in the output layer identifies the letter that the deep neural network sees. In the case of the image, our trained neural network returns an accurate value of 3. Now that we have a better understanding of what the MNIST dataset is and how it's classified, we need to further discuss its performance theory before moving on to designing our very own neural network for classifying this dataset.